In this video, we're going to take a look at heterogeneous aqueous systems, suspensions, colloids, the Tyndall effect, and Brownian motion. So we already discussed solutions, which have the small sized particles and are evenly distributed throughout its dispersing medium. On the other end, we have suspensions. They have the larger sized particles. They will settle out upon standing. So that's because those particles being so much larger, gravity takes over and they will then again settle out to the bottom and separate into layers. They're not small enough to stay dispersed throughout the medium which they are in, which again often is water. Those particles in a solution again are much smaller, only about 1 nanometer in size, while those in a suspension are as large as 1,000 nanometers. So a common suspension you probably can think of is like Italian dressing, where you have to shake it to keep it all mixed together, but then over time, as the particles begin to stick together and make larger blobs, will continually then separate into different layers. In between those two is a colloid. Colloids have intermediate sized particles between 1 and 1,000 nanometers in range, and they will stay mixed together. They don't settle out like we saw with the suspension, and the dispersion medium can be either a solid, a liquid, or gas, and what is being dispersed also as a solid, liquid, or gas. And again, because they have smaller sized particles than that of a suspension, then they will stay spread throughout. Some common colloids that you've probably seen and didn't even realize are whipped cream. And in whipped cream, you have a liquid that is dispersing the gas. We have marshmallow, which is a solid dispersing gas. Fog, which is a gas with little particles of water, liquid particles of water dispersed throughout it. And smoke, again, you have a gas that's dispersing little small pieces of ash, little solid pieces. Both suspensions and colloids exhibit what we call the Tyndall effect. They scatter light of particles that we can see the beam of light as it travels on through. Again, we've kind of noticed this probably in the past, not something you even thought about, but if you run light through water, you don't even notice the light as it goes through water. You can see it come out the other side, but as it goes through the water, you don't notice it at all, because water is either a pure substance, distilled water, or a solution like in tap water or even ocean water. But in a colloid, where now you have much larger sized particles being dissolved in, that light beam gets spread out, as you see in the background of this picture, the fog kind of through the trees. You see the light coming through the trees because of all the little water droplets that are there dispersed throughout the air. And then in a suspension, even more so, where you have those particles that are dispersed throughout, again, are now exhibiting the light as it travels on through. Both colloids and suspensions also exhibit what we call Brownian motion. As the particles are chaotically moving around, we're able to see that motion as that light shines on through, and you see kind of those flashes or scintillations of light because of how those particles are bouncing around off each other. And as these particles collide with each other and they reorientate and they rotate, that's why again you catch these flashes of light, because of the way they collide with each other and catch the light just right. Those collisions help keep these colloidal particles from settling out, again, unlike that of a suspension, because as they bounce off each other, it keeps them dispersed throughout the medium which they are in. And as these particles are bouncing around, they absorb these ions from what they're being dispersed throughout, and therefore it actually gives them a charge which keeps them repelling away from each other. And that those absorbed particles with those charges, again, like charges repel, keeps them from being able to coagulate together. Unlike that of a suspension, where they're able to keep growing to larger and larger blobs and eventually into a whole layer of just one substance, we don't see that in a colloid because, again, those oppositely charged particles bouncing off each other, or therefore repelling each other and keeping them from settling on down. They will always absorb the same charged particles. Either it's going to absorb negative particles or positive particles, but that substance always absorbs the same particles, so therefore you always have repulsion. You don't have coagulation in colloids. You can add a coagulant, which then will be something of an opposite charge than they normally absorb, and therefore allow them to now stick together and make larger particles. That's kind of how you filter out some substances that you don't want, by adding in this coagulant to now make those particles stick together, so that way they are large enough that they can be filtered on out. Otherwise, particles in a colloid are too small to be filtered. Only particles within a suspension have large enough size particles that could be filtered on out. Again, colloids, if you think of like fog, you can't just run a filter through fog and remove all the water out of the air. That water, again, would be too small to fit through a filter, So solutions and colloids can't be filtered out, just those, again, of suspensions. And lastly, we have a special type of colloid. It's called an emulsion. An emulsion is a liquid that is dispersed throughout a liquid. So in the 4 examples of colloids before, there were none of that fit in this category because they have their own special category. You have a liquid, again, dispersed throughout a liquid. Kind of like oil in water. You can make an emulsion out of oil and water, but you need to add in an emulsifying agent. So adding in a soap or detergent that has a polar end and a non-polar end actually allows that oil and water to stay mixed, because the emulsifying agent gets between those two things and keeps them from repelling, it keeps them from coagulating together, and allows it to stay mixed continuously. That polar end would be, therefore, attracted to the water molecule end, and the non-polar end would be connected to the oil or the grease end, allowing it to now make those two things mix. Two immiscible substances that normally don't mix together now could mix together. We see that with, again, milk. So the fat used to separate away from the cream, and you'd have that cream layer on top. The old saying, the cream rises to the top. So when you used to get your milk actually delivered from the milkman, you have to shake your milk and have it mixed up. But now you don't have that issue anymore because the milk is homogenized. They take that milk and through a process, they split up all that little fat globules, make them to much smaller pieces, add an emulsifying agent, and allow them to stay mixed together.